Hello everyone and welcome to lectures on modern C++. In this video tutorial we are going to explain what are the smart pointers in C++. In particular we are going to focus on unique pointer. First of all, let's explain the need for smart pointers. When allocating or reserving the memory on heap using row or standard pointers, we need to manually deallocate or free this memory by calling delete operator. However, number one, we can forget to include a delete statement in the code, and number two, an exception or an execution error might occur before delete operator. In these and similar cases, we create memory leaks that can lead to instabilities. To avoid this and similar problems, we use smart pointers. And let's immediately code an example that will illustrate the need for smart pointers. Namely, I'm going to create an example that will create a memory leak. Okay, so let's start with coding. Here's the general idea. The general idea is to declare a class, then inside of a new function, we are going to instantiate, or better to say, to create objects of this class on the heap. However, we will deliberately avoid calling the delete operator inside of that function. This will create a memory leak, as you will see later on. So let's start with coding. First of all, let's start with the standard include statements, input output stream, string, and using namespace std. So let's declare a class. I'm going to call the class as student. This class can, for example, store student name, student GPA, and it can be used in some database. So let's start with declarations of public and private member variables and functions. Here we will only store the student name. So let's write this. And let's start with the default constructor. The default constructor should have the same name as the name of the class. And over here, we're going to print this statement, constructor called. Here it is. Okay, and then let's end line. The purpose of printing this statement is to help you to visualize once an object of a class is being created. Good. Let's now verify that we don't have any errors or declaration issues. Currently no issues. Okay, let's create two additional functions or three additional functions. First of all, let's declare a destructor. Destructor will be automatically called if the object of the class is being destroyed. So let's do this, and let's type destructor called. Okay, again, I'm printing the statement such that you can visualize if a destructor is being called. And then let's provide two standard functions. Let's provide the setter and getter function. So let's first start with the setter function. So let's type void set name. This function will set the name of the student. So here it is. And then over here, I'm going to simply type student name is equal to name. Here it is. Let us fix this alignment. And let's provide a getter function. Let's type something like this. And then over here, let's type cout student name is, and then let's print the student name over here, and then let's end the line. Okay, that's it. This is a minimal implementation of a class. Next, let's test this class inside of our main function. So what I will do over here, I'm going to declare, or better to say to instantiate an object of this class. I will call it a student1. Here the default constructor should be called, and then let's just set the name set name, and then let's set the name John dough. And then finally, let's get the name. Here it is. Get name, and this is it. This is a minimal test example that will test our class. Good. Let's double check for errors. These are the errors from a different example, so let's ignore this. So let's save this, and let's try to compile this. Here, as you can see, I'm using a simple command line to compile, and I will be using G++. So here is the syntax. First of all, let's see all the files and folders, and let's see the name of the file. It should be memory leak 1. Okay, so let's see, it's here. So let's type this thing. So let's call G++ compiler, and let's provide these parameters. WAL means that we want to provide all the warnings while compiling. That is, the debugger or the compiler will print all the warnings if they exist. And then what do we need to do? We need to provide the source file name. The source file name, as you can see over here, is memory leak 1. So let's type this. And then let's provide the output file. Let's call the executable file as memory leak 1. And let's see what will happen. No errors. So let's now call memory leak 1, and let's analyze what's happening. First of all, we can see that the constructor is called. Good. This corresponds to this line over here. Then we are setting the name. Here, nothing is being printed. However, here we are printing the name. This is the statement. Let me just add the space over here. And then over here, we are calling, or actually the destructor is being automatically called. Note over here that we didn't explicitly call the destructor. The destructor is being automatically called. Why is that? Well, this is a main function, and all the variables and objects are actually created on the stack. When something is created on a stack, it is automatically being destroyed once the program completes. That's why we don't need to explicitly call the destructor, since the destructor will be automatically called, as you can see over here. Now, let's create a memory leak. Here it is. The basic idea is to declare a function. So let's call this function like this. Manipulation function. Okay. And inside of this function, let's create, or better to say, let's instantiate an object of this class on the heap. To do that, we need to type something like this. And then over here, we need to type this. Here, I'm using the new statement. And the new statement will actually reserve the space for this class on the heap. Heap is a different memory storage from the stack, as you will see later on. However, the difference between stack and heap is that on heap we have to manually destroy objects. That is, the objects will not be automatically destroyed, and that's why we need to use the delete statement. To create the memory leak, let's first do something with our student. This is actually a pointer. pStudent is a pointer to the memory address on the stack in which student is being stored. And let's do something like this. So let's again set name. Let's call the name as Jane Doe. And then over here, let's do this. pStudent. And let's get the name. Let's get the name, and that's it. And note over here that I'm not calling the delete statement. And you will see that the destructor of our pStudent is never being called. And this is the issue. Now, let's save this, and let's call this function from our main function. So let's do something like this. And let's print a statement before. Let's do something like this. Calling the function that creates memory leak, and then let's do the end line, and let's call the function. Let's save this and let's go back to our terminal. Let's compile again and let's run it. Oops, I didn't run the correct file. Okay, and here it is. So let's analyze again what's being done over here. So let's analyze. First of all, constructor is being called. However, this is the constructor of student1, which is created on the stack. Then here we are setting the name of student1, and then we are getting the name of student1. Then here's the print statement where we're calling the function that will create the memory leak. And so let's see what's happening over here. Constructor called. Well, this line corresponds to this particular line. So the constructor is being called. Then the name is being set. The name is being printed out. As you can see, sent and printed out. And let's analyze what's happening. Here you can see some destructor is being called. However, this is not the destructor of P student. This is basically the destructor that's being called once all the objects inside of the main function are being destroyed. That is, this is the destructor of student1. So keep in mind that. And you can see that after student name is Jane Doe, this function returns. That is, it destroys P student. However, the memory reserved for our student is still somewhere out there. However, we lose access to that memory. And the destructor of our particular object is not being called. That is, this creates an issue. And over here, you need to call delete P student in order to free the memory space. That is, whenever you use row pointers, and here's the row pointer to the student class, you need to manually call delete. Often people forget this, or the code is too complex and people cannot track delete statements, and they cannot track how many objects are being created and when they're being destroyed and when they should be destroyed. Or some exception can occur. For example, even if you have this delete statement, you can have a try and catch statement or something like that, or some exception can occur or some error can occur, and this delete statement, although it exists, it will never be executed. Consequently, that's why we use smart pointers. However, before we go again and continue our discussion on smart pointers, let's save this and let's run this once again. So let's now compile this and let's run it. And we can see clearly what happened after student name is Jane Doe. The destructor is being called, and this destructor is actually being initiated by this delete statement. Okay, so let's go back. First of all, you should keep in mind that in modern C++ books, you will often see something along these lines. To avoid problems with memory leaks and similar problems, the modern C++ programming language strongly discourages the use of row or standard pointers except for some cases. Instead, programs and programmers are encouraged to use smart pointers. In this lecture on modern C++, we briefly explained the smart pointer called unique pointer, and we explained how to use it in C++ code. We do not plan to cover all the caveats of smart pointers, but instead we focus on the basic concepts that will explain you how to use them. First of all, let us clarify what are heap and stack storages. In C++, heap and stack are two memory regions. Memory and stack is automatically managed by the compiler. This means that the memory is automatically allocated and deallocated. Typically, local variables, function parameters, and return addresses are stored on a stack. When we call a function, memory space for its variables and other function objects is automatically allocated or reserved on the stack. This memory is automatically deallocated or freed when the function returns or ends. That is, the local variables inside of the function go out of the scope. And this is what happened in the previous example. So let's look inside of this example and let's explain what's happening over here. Here we have a function that adds two integers. So what happens? First of all, we declare an integer c, and when we do that, this integer is declared on the stack. Then we add two integers and then we return the value c. However, once this function returns, this memory on the stack is being destroyed. That is, it disappears. Now, this is very, very important to engrave in your mind. When the function returns the value, the memory and stored value are deallocated or erased. Although here we are returning the value, we are returning the copy of this value, which is probably stored in some other variable. The memory is managed by using the system, and the complete process is very fast. That is, stack or storing and reserving memory addresses on the stack is super fast. Stack operates like a stack data structure. That is, memory for variables is pushed at the top of the stack and popped when the stack is clear. And here's one example. Let's say that we have A, B, C, and we want to store these variables and corresponding memories in stack. So first of all, we start with A. A is in, then B is declared, so the B is in, then C is declared, then C is in. When the function returns, we go vice versa. First of all, we empty C, that is, C is out, or pop out C, then we pop out B, and then we pop out A. And that's the basic idea. Here are a few other important things and facts about stack. Stack has a fixed and relatively limited size that is determined at the program at the startup. Then, the stack is typically in the CPU cache. Exceeding this limit leads to the phenomenon called stack overflow. For example, if you call a function recursively many times in every call, memory will be reserved. In this way, you can run out of the stack memory. And here's the phenomenon. Every time you call a function, you will reserve a memory space represented by this rectangle. Then you call recursively this function again. New memory space will be reserved. However, the old memory space will still be there. And if you repeat this procedure, that is, if you're calling the function recursively many times, you're going to reserve a lot of memory space and you might run out of stack memory. On the other hand, memory on the heap space is dynamically allocated and deallocated by the programmer by using new and delete operators. The allocation and deallocation of memory on the heap are slower than the same operations on stack. Variables and objects on heap exists beyond the scope of the function, unless we call delete. The heap space can dynamically grow and shrink during the program execution, that is, during the run time. And here is one example. Here, similarly to our previous example, we are declaring a pointer to the type int, and then over here we are reserving space on the heap in order to store the value. Then here we are storing the value 10 on the heap, and that's the general procedure. To summarize, in this particular example, the memory to store P is allocated on the heap. To free this memory, we need to call delete. And let's construct again a simpler example compared to the example that we explained at the beginning of this video tutorial. So what's happening over here? Here's our function. We are reserving memory space on the heap and returning the pointer to that memory space. Then here we are adding the two numbers A and B, and we are storing the value on the heap, and then we are printing the value. Here, the issue is that after function returns, the memory on heap is not deallocated. The pointer to that memory space is lost once the function returns. So let's analyze this example. P will actually be destroyed. However, P is a pointer, and P is actually declared on the stack. However, the memory for storing the value that P points to is reserved on the heap. And keep in mind this. P itself will be destroyed. However, this reserved memory will not be free. freed, and this is very, very important. So to solve this problem, as explained previously, we will add delete here. So before we return the value, we are just going to delete p, and that's it. Issue: what happens if delete is never executed? You can add delete, however, you can have some code block over here that throws an exception and you never reach the statement delete p. That is something happens over here, the program breaks, it doesn't execute this, or there is some chaining in your program which never produces or comes to this line, and that's the issue. Solution: we use smart pointers. In this particular tutorial, we are going to explain the unique pointer, which is one of the smart pointer types. There are also other types, and to use this pointer, we need to use the header file memory. That is in your file, on the top of your C++ file, you need to include memory. So here's the previous example by using include with unique pointer. First of all, I included input-output stream memory using namespace std, and here's our second function. And here's the declaration of our unique smart pointer. You type unique pointer, then you have to specify data type. The data type is int. Those of you who are familiar with C++ templates will immediately see that unique pointer is actually a template. This is very important to keep in mind. That is, unique pointer is actually a class, as you will see later on, and here you need to specify a data type to which this pointer points to. And then over here you specify the name is p, and inside you put new int. Here you are actually calling the constructor of unique pointer, and you are passing memory space. That is, new int will reserve the memory space on the heap. However, p will be on the stack. That is, you're controlling memory space on the heap by using variables on the stack. And automatically, when this function returns, what will happen? P will actually automatically be destroyed. However, not only p, but also the memory allocated on the heap. That is, the destructor of p will be called and this memory will be erased. And that's the main idea. Note over here that you can use smart pointers similarly to standard pointers. That is, you can dereference by typing, or reference by typing star p if you want to store the value in p, and then you can print it out like this. That's it. Simple as that. There is another way to declare unique pointer. You can use make unique. So the first part is the same, and then you specify make unique, the data type, and over here I'm initializing the memory space with 0. That is, in this way you can in a more convenient way reserve the memory space, and then over here you store the value and you print the value. We can also use the smart pointer on classes and other objects, and over here is an example similar to our previous example. So here's our class students, and you can declare the class similarly to what we did, and in int main you can declare the smart pointer like this. You call unique pointer, you specify the data type or the class name student, then you specify the name of the pointer, and then you call new student to reserve space. And then you can also use this way of declaring a smart pointer. That is, you can use make unique. That's it. Later on, we are going to modify our example to explain how to implement them in practice. So let's summarize smart pointers. A smart pointer is a class template that is declared on the stack and initialized by using a pointer that points to the memory on a heap. That is, whenever you write something like this, the memory is reserved on the heap. However, you get the ownership through this pointer p to that memory. That is, we can say that the smart pointer p owns the memory on the heap. However, the p is declared on the stack. The smart pointer will automatically delete the memory that the row pointer points to. That is, we don't need to use the delete operator. Keep in mind this. Inside of the destructor, smart pointer is a class template, keep in mind, and inside of the destructor of the smart pointer there is a call to delete that releases the memory. That is, once the smart pointer goes out of the scope, a destructor is being called that destroys the memory. Since the smart pointer is declared on stack, its destructor is automatically called when the smart pointer goes out of the scope, even if an error or an exception is thrown somewhere. This means that it is guaranteed that the memory is deleted. This is very important to keep in mind. The philosophy of smart pointers is to give control or to give ownership of any memory resource reserved on a heap to an object, that is, to a smart pointer on the stack. The destructor of the object on the stack contains procedure to free the memory once the object goes out of the scope. Next, let's modify this example and let's explain how to implement unique pointers. First of all, at the beginning of the file, you need to include memory. So don't forget to include the memory header file, otherwise you will not be able to use smart pointers. Then over here, let's declare a function. I'm going to call this function as manipulation function 2, and let's use the first form of declaring smart pointers. So here, I'm going to type this. Then I'm going to specify the type name. The type name is student, since this pointer will point to the object of the class student. And I'm going to declare a pointer. I'm going to call it sp student. And then over here in the first form, you simply type new student. What happens over here is that we are reserving the memory space on heap and returning the pointer. This pointer is used to initialize, or better to say, to instantiate this smart pointer called SPS student. Good. Now let's do a few things over here. So let's SP student. Now we can use the standard notation for pointers. Let's set name. Let's call the student as AH, for example, Alexander Haber. And then over here, let's get the name. Let's get the name, and that's it. Okay, so this is the first form of declaring smart pointers. Again, we specify type, and over here we reserve the memory space and we save. Now let's modify this main function. I'm going to simply comment these lines since we will not be using them anymore. And then over here, I'm going to simply call manipulation function 2, and that's it. So let's test this and let's see will this work in practice. So let's do this, and then let's save, and let's go back to our terminal. In the terminal, let's compile this file and let's run it. So let me see the name. Here it is. Constructor called, student name is AH, and notice over here that the destructor is automatically called. That is, once this pointer SPS student goes out of the scope, or before it goes out of the scope, the destructor of the class is called, and this destructor frees this memory space. Simple as that. Let's explain the second form of the declaration. Here again, I'm going to call the function as manipulation function. However, here I'm going to change the number to 3. And again, we do unique pointer. Then the class name is student. And over here, again, I'm going to call the pointer sp student. And then over here, I'm going to use the second form of declaring the pointers. I'm going to use make unique. And then I'm going to specify class. And then over here, I'm going to just type something like this, and that's it. And here I made an error. It should shouldn't be make. Let me now, I made a spelling error here. Let me correct. Unique. Let me see. Yes, make unique. That's it. And then again, let's again do something like this. BH, for example, or SH. Or let's change this name. For example, SL. For example, initials of a student. And over here, I'm going to comment this. And then I'm going to call simply this function, save this. Let's go here. Let's compile, and then let's run memory leak, and you can see constructor called, student name, and destructor called. That is, we are inside of this function, and the memory is being automatically freed once the function returns. Okay, that's all for today, and I hope that you enjoyed this video tutorial, and see you in the next video tutorial.